Jai students, welcome to my YouTube channel. Students, always think not of yourself as the architect of your career, but think yourself as the sculptor. Expect to have to do a lot of hard hammering and scrapping and polishing. So students, what I mean to say is that if you don't go after what you want, you will never ever have it. If you don't ask, the answer will be always no. So if you don't step forward, you will obviously be always in the same place. So keep pushing yourself harder and harder, right? So with that students, let's begin today's session. In this particular session, we are going to discuss some numericals based on friction. In all these numericals, we'll consider the force of friction to be present between the two surfaces in contact, right? So, let's start with the first question. First question is, students, a heavy uniform chain lies on a horizontal tabletop. It's like this. This is a tabletop. Let us assume this to be a tabletop. And a heavy chain is lying like this. This is a chain. And it is lying with some portion hanging over one edge of the table like this. It's hanging like this, some portion, right? So what we are supposed to do is the coefficient of friction between these two surfaces in contact is given to be 0.25. Now we are supposed to find out the maximum percentage of the length of the chain that can hang over one edge of the table, right? So this is, the system must be at rest. It should be in equilibrium, right? So what we consider is, let us consider the total length of the chain be L and its mass is M, right? Mass is considered to be uniformly distributed over the chain. So total mass of the chain is N, total length of the chain is L. Suppose X portion of the chain is hanging over the edge of the table. So the portion L minus X of the chain will be on the tabletop as shown in the figure, right? So students, the same diagram can be represented in this manner, right? The same diagram can be represented in this particular manner. In place of this part, L minus X, we'll consider a block, right? And suppose this is a massless and frictionless pulley, and this is an inextensible string like this. And this part may be represented by another block. Now, what will be the mass of this block? Let's make use of unitary method, students. For length L, the total mass of the chain is considered to be M. For unit length, the mass is M by L. Therefore, for portion X, the mass would be M by L into X. So, this block represents a block of mass equal to the mass of portion X of the hanging chain. So its mass is M by L multiplied by X. Isn't it, students? So for unit length, mass is M by L. So for length L minus X, the mass of this portion of this chain, which is on the tabletop, which is represented by this block, it would be M by L multiplied by L minus X. Clear, students? So I have represented this hanging part of the chain with this block of mass M by Lx, while I have represented this part of the chain which is lying on the tabletop by this block of mass M by L multiplied by L minus X. I have considered this pulley to be frictionless and massless. This string is also massless, so that the entire mass of the chain is distributed between these two blocks, right? So now the question arises is, what are the forces acting over here? It would be M by L X into G. This is the weight. Here its weight would be M by L L minus x into g. Weight always acts in the vertically downward direction along the radius towards the center of the earth, and the normal reaction, it will be along this direction. Right? It will tend to move along this direction. This hanging part will make the rest part of the chain to slide towards this direction, isn't it? And this being prevented by the force of friction, which will act in a direction opposite to which the body tends to move. Right? And this is the force in between. So it may be considered to be F dash. Right? Now let's construct the equation. Right? So for this body, F dash, or it may be considered with tension, in this case it may be considered with the contact force. Right? It is m by L xg, since the system is at rest. Right? Also, F dash, it must be equal to small f, force of friction. And force of friction, you are aware, it's equal to mu into r. Make use of the laws of friction, isn't it? So F dash is equal to small f is equal to mu. R is balanced by m by L minus x into g. Clear, students? So now, equating these two, from these two equations, what we get is, therefore, mu m by L minus x into g is equal to F dash, which is m by L x into g. So m by L get cancelled, g and g get cancelled. So what we get is mu capital minus x is equal to x, right? The value of mu, students, the value of coefficient of friction, it's given to be 1 by 4, isn't it? So it is 1 by 4, L minus x is equal to x, or L minus x is equal to 4x. Therefore, 5x is equal to L, or x by L is equal to 1 by 5. So students, this is the fraction of the length of the chain which can hang over one edge of the table. Clear? But here we are supposed to find out the maximum percentage of the length of the chain. So this is the fraction. In order to convert it into percentage, we need to multiply it by 100. Therefore, the percentage of the chain which is hanging over the edge of the table, it would be 1 by 5 multiplied by 100. So it will be equal to 20%. So this is the answer. So 20% of the length of the entire chain can hang over one edge of the tabletop, right? So that the entire system remains at rest. It remains at equilibrium of rest. So this is the solution. So basically you can convert it into two blocks connected through a string, massless string, over a pulley which is again massless and frictionless. So that is how you can construct the equations and get the result, right? Okay, let's proceed to the next question then. Second question, students, it's pretty important and it's a very, very good question. Let me read out the question for you. Question is, a piece of ice slides a 45-degree incline in twice the time it takes to slide down a frictionless 45-degree incline, right? So again I repeat, a piece of ice slides a 45-degree incline in twice the time it takes to slide down a frictionless 45-degree incline. So we are supposed to find out the coefficient of friction, right? We are supposed to find out the coefficient of kinetic friction. It's the case of the body sliding down, right? So it's a pretty important question. So let's try to do it. So basically here what we are supposed to do is, we'll consider two cases. This is an inclined plane which is smooth. So here the coefficient of friction is 0. Force of friction is absent. And this is another case, same 45-degree incline, but it offers some sort of friction. So it is a rough inclined plane. Right? In both the cases, the block, while coming down the plane, will have covered the same distance. Right? This is it. Okay. Now what to do is, suppose in this case, the acceleration is A1. In this case, the acceleration of the block is A2. Clear, students? Suppose in this case, the block covers displacement S. Here also, the block will cover displacement S only. More or less it will be same. Suppose the block takes time T1 to cover this displacement S, and here the block takes time T2 to cover this displacement S, right? Initially the block is at rest. So let's find out the relationship between the acceleration and the time, right? So from first equation of motion, we know S equals to ut plus half at square. Actually, this is the second equation of motion, which is the displacement time relationship. S is constant in both the cases. U is 0. So since U is 0, therefore S is equal to half a t square, or A is equal to 2S divided by t square. Therefore, students, A1 by A2. S is common, 2 is common, so it will be equal to T2 square divided by T1 square. Am I clear? So this is the relationship between the acceleration and the time taken the block to slide down to the bottom of the inclined plane, right? And it's given a piece of ice slides a 45-degree incline in twice the time it takes to slide down a frictionless 45-degree incline. So here, obviously, the time taken by the block would be twice the time taken in this case. So it is given T2 is equal to twice T1. It's given. In the case of the rough inclined plane, in the case of this rough inclined plane, the time taken by the block to reach the bottom is given to be twice the time taken by the block in reaching the bottom in the case of a frictionless inclined plane, right? So what we get? T2 equals to twice T1. So it will be equal to 4. Substitute the value of T2 as twice T1, so its square would become 4 T1 square by T1 square, so we will be left with 4. That is, A1 is equal to 4A2. Right? This is to be used. Okay, students? Okay, now what we do is, let's draw the free body diagram in each case and get the relationship between A1 and A2. Right? Okay. Let's draw the free body diagram now. Let's consider the case of the smooth incline first. Okay. Let's draw the free body diagram for this one. It is like this. This is the block. In this case, the force of friction is absent. So what are the forces acting over here? It is mg. Let its mass be m. We are considering the same block, isn't it? So reaction would be acting perpendicular to the surface over which this block is placed. mg can be resolved into two components, isn't it? This would be 45 degree, obviously. So mg can be resolved into two components. This will give us mg cos 45 degree, and this component, it will give us mg sin 45 degree, right? So acceleration is along this direction. Frictional force is absent. So what will be the equation for this? R will balance mg cos 45 degree. So the net force acting on this block is mg sin 45 degree. This is the net force acting on this block. And as per Newton's second law, net force acting on a block is mass into acceleration. So its mass is m, acceleration is a1. So put this as equation 1. M get cancelled. So A1 is equal to G sine 45 degree. Right? Put this as equation number 1. Clear, students? Similarly, let's find out the relationship for A2. A1 here we have obtained is 4A2. Right? This is the relationship between the acceleration in the two cases. Now let's draw the free body diagram in this particular case. This is case 1 and this is case 2, suppose. This is the inclined plane. This is the block of mass m. So one is the force acting as the weight. Other one is the reaction. Now mg can be resolved into two components. This angle would be 45 degree. So this component would be mg cos 45 degree, while the other component would be mg sin 45 degree. So it will tend to get accelerated along this direction, down the inclined plane. So as the body tends to move along this direction, force of friction will act in the opposite direction. Clear, students? Here is the case of a rough inclined plane. So the force of friction is to be considered. So R is mg cos 45 degree, no doubt regarding this. R is mg cos. Okay, R is mg cos 45 degree, right? And what about these two? These two are unbalanced forces. The body is getting accelerated over here. So mg sin 45 is more or dominating as compared to frictional force. Therefore, the equation will be net force is mg sin 45 degree minus force of friction. Right? It is equal to, net force is equal to mass into acceleration. Mass into acceleration is A2. Now let's substitute the value of force of friction. It's mu r. So it will give us mg sin 45 degree minus F is equal to mu r. R is the normal reaction, which is mg cos 45 degree is equal to m A2. Right? M get cancelled. So what do you get? A2 is equal to G sin 45 degree, that is 1 by root 2 minus mu G, again cos 45 degrees, 1 by root 2. Put this as equation number 2. So we have obtained both the value of A1. A1 is G into 1 by root 2. Sin 45 degrees, 1 by root 2. So we have obtained both the value of A1 and A2. Now students, the last step. Simply substitute this value of A1 and A2 over here and we should get the result. Right? So let's try to find out the coefficient of friction then. Simply substitute the value of A1 and A2 in this particular equation. Okay. A1 is G by root 2. It is 4 times A2. A2 is G by root 2 can be taken as common. Right? And over here we will be left with 1 minus, over here it's mu. So G by root 2 get cancelled. So we get 1 by mu is equal to 1 by 4. Or mu is equal to 1 minus 1 by 4. So that will give us 3 by 4 or 0.75. So students, this is the answer. This is the coefficient of the friction between the two surfaces in contact. Right? So this was a very, very interesting question. Initially, you need to consider the equations for both the cases, and then in the case of rough incline, you need to consider the frictional force. Right? So we are over with question number 1 as well as question number 2. Now let's proceed forward and let's attempt question number 3 then. Okay, question number 3 is pretty simple one. Question number 3 states that a body on a rough incline, obviously means that the inclined plane is offering some force of friction. Okay, a body on a rough inclined plane just begins to slide. It just begins to slide when the slope of the plane is 1 in 4. This is very important, students. You need to understand this statement. 1 in 4. Calculate the coefficient of friction, right? It's pretty straightforward question, but it is based on your theoretical knowledge. In order to solve this question, you should be very, very clear about the concept of angle of repose, right? So let's do it. This is a rough inclined plane, and suppose this angle is theta, and a body placed over here just begins to slide. It is on the verge of motion. This body is on the verge of motion. So this theta is known as angle of repose. Students, you must remember in the theoretical portion we have done this topic. Angle of repose may be defined as the angle which this inclined plane makes with the horizontal, at which a body placed over it just begins to slide. That is, the body placed on the inclined plane is on the verge of motion, right? So, in that case, we have proved that the coefficient of the friction is equal to tangent of the angle of repose. We know that. This we have already proved. So, in this question, we are supposed to make use of this formula directly, right? So, the coefficient of the friction is numerically equal to the tangent of the angle of repose. Theta is the angle of repose. Now, students, the slope of the plane is 1 in 4. 1 in 4 means it's actually 1 perpendicular and 4 units hypotenuse. 4 units hypotenuse. So actually 1 in 4 means sin theta is given. It is perpendicular by hypotenuse. Will you remember this? 1 in 4. 1 unit perpendicular, 4 units hypotenuse. Right? 1 in 4. So it is actually sin theta is given. Sin theta is equal to 1 by 4. Please do remember this concept. Okay, if sin theta is known, we can easily find out the value of tan theta, isn't it? So this is 1, this is 4. So using Pythagoras theorem, this base would be given by square root of 4 square minus 1 square. So it will be equal to square root of 15, isn't it? So in this case, base it will be equal to square root of hypotenuse square minus perpendicular square. Make use of Pythagoras theorem. So the magnitude of the base, it would be equal to 16 minus 1, that is root 15. Therefore, students, tan theta, it's perpendicular by base. So it is 1 by base is root 15 units. And since mu is equal to tan theta, therefore, from these two we conclude that the coefficient of friction between these two surfaces in contact is known as 1 by root 15. Now, since the body is on the verge of motion, it will be actually the coefficient of limiting static friction, right? So this was a very, very interesting question. So students, we are over with question number 3 as well, right? Let's proceed to the last question then. Let's proceed to question number 4. Okay, question number 4 is a horizontal force of 12 kgf. kgf is the gravitational SI unit of force. It is kilogram force. It can be also known as kilogram weight. It's the SI unit of force, gravitational SI unit of force. So horizontal force of 12 kgf pushes a block weighing 5 kgf against a vertical wall. So the situation is like this. This is a wall. This is suppose a wall, right? And this is a block over here. This is a block. A horizontal force of, this is the horizontal force which is applied. This is the horizontal force which is 12 kgf. So, whatever force is applied, the same force will be exerted by the wall on this block, and that is known as normal reaction, isn't it? That will be known as normal reaction. So this is normal reaction. It will act along this direction, right? And the weight of this body obviously will act along this direction. And it will tend to slide, it will tend to move along this direction, it will tend to fall. So force of friction will act along this direction, right? So if you draw the free body diagram of this case, then it will be like this. This is the block, this is the normal reaction, right? This will be the force of friction, and this will be the weight. These are the three forces acting on this body which is pressed against the vertical wall, right? And we are aware, students, in case of a body placed against the vertical wall by applying a pulling force, by applying a horizontal force, then in this case weight of the body will have no role to play in its friction. So in this case F is equal to mu r, normal reaction, right? So as per the laws of friction, F is equal to mu r. Obviously a normal reaction is not equal to the weight, right? It is equal to this applied force which is applied along the horizontal direction. Here R is equal to 12 kgf. This horizontal force may be considered to be the action, and the force exerted by the wall on the block, it may be considered to be the reaction force. So reaction force would be equal in magnitude to that of the action force, right? So here reaction force is 12 kgf. So let's first find out the force of friction. Now first part is, will the block slide down against the wall? And we are supposed to consider the block was not moving initially. So case A. It is not moving, so we are supposed to find out the static friction. So in this case, we need to consider the coefficient of static friction. So what is the coefficient of static friction? It is 0.5. Multiplied by what is R? It is 12 in kgf. So it will be equal to 6 kgf. So therefore, Fs, the static friction in this case, which is 6 kgf, is greater than the weight. Weight of the block is given to be 5 kgf, isn't it? So friction being greater than W, therefore the block will remain at rest. The block will remain at rest. It will not fall. Clear? It will not fall in case 1. Now let's consider case B. Case B, will the answer change if the block was initially sliding? Let us consider the block to be initially sliding like this, right? So in this case, we need to consider the kinetic friction. So it will be equal to mu k into R. Mu k is the coefficient of the kinetic friction. And coefficient of kinetic friction, it is somewhat less than that of the limiting static friction. So here its value is given to be 0.4 multiplied by 12. So it is 4.8 kgf. Now in this case, students, the kinetic friction is less than the weight of the block. The weight of the block is 5 kgf, while the kinetic friction when it is initially sliding is found to be 4.8 kgf. So weight is greater than that of the kinetic friction. So it will keep on sliding. Clear? In the second case, it will keep on sliding. Therefore, the block will keep on sliding. So that's the answer, friends. So we are over with all the 4 questions. All the 4 were selected questions. I hope you have understood the concepts involved in each of these 4 questions, right? So that's it for this particular session, students. Do join me in my next lecture. I'll be coming up with some more interesting numericals. Till then, goodbye and do take very good care of yourself. Thank you.